First question, modulus of rigidity of ideal liquids is infinity, 0, unity, some finite small non-zero constant value. So we know that within limits of proportionality, the ratio of tangential stress to the shearing strain is called modulus of rigidity of the material of the body and is denoted by this eta. In this case, the shape of a body changes, but its volume remains unchanged. Consider a cube of material fixed at its lower face and acted upon by a tangential force F at its upper surface having area A. Only solids can exhibit a shearing as these have definite shape. In liquid, eta is equals to 0. So the frictional, that is viscous force, cannot exist in case of ideal fluid, and since they cannot sustain shearing stress or tangential force are 0. So there is no stress developed. So correct answer for this question is option B, that is 0. Moving towards the next question. The temperature of a wire is doubled. The Young modulus of elasticity. So we know that the Young modulus Y is defined as a ratio of normal stress to the longitudinal strain within the limit of proportionality. So we can write the formula for Young's modulus as Y is equals to normal stress, that is F upon A, the whole longitudinal stress, that is delta L upon L. So I can write this equation as FL upon A delta L. The fractional change in the length of the material is defined as delta L upon L naught, which is equals to alpha delta T, where delta T is the change in the temperature, L naught is the original length, alpha is the coefficient of linear expansion of the given material, and L naught is the original length of the material. So simply change in length is due to change in temperature, that is delta L is equals to L naught alpha delta theta. Okay, and the Young modulus, that is Y is equals to stress upon strain, which says that F is equals F of L upon A delta L. Delta L, I can put this value over here, so I can get F L naught the whole upon A L naught alpha delta T, and from here I can say that Young modulus is inversely proportional to temperature. Okay, so when temperature increases, delta T increases as difference, and hence Y decreases. So Young modulus of elasticity will decrease, and that is there in option D. So correct answer for this question is option D. Looking towards the next question. A spring is stretched by applying a load to its free end. The strain produced in the spring is. So according to the diagram, where a spring is suspended with a fixed rigid support, now a load is attached with the lower end of that spring. So it's stretched by applying a load to its free end. Clearly the length and shape of the spring changes, and the weight of the load behaves as a deforming force. The change in length corresponds to the longitudinal strain, and change in shape correspond to the shearing strain. So correct answer for this question is option C, that is longitudinal and shear strain. Looking towards the next question. A rigid bar of mass m is supported symmetrically by 3 wires, each of length L. Those at each end are of copper, and the middle one is iron. The ratio of their diameters, if each is to have the same tension, is equal to. So as the bar is supported symmetrically by the three wires, therefore extension in each wire is same. Let T be tension in each wire and diameter of the wire is D. then Young modulus is given as Y is equals to stress upon strain, which is equals to F by A the whole upon delta L by L. So I can write Y is equals to FL upon A delta L. Now A and delta L, A can be written as FL upon pi d by 2 the whole square into delta L. Okay, and this 2 when shifted above, 2 square, it gives out to be Y is equals to 4 FL the whole upon pi d square delta L. Okay, now if I separate d square from here, so it gives the equation as d square is equals to 4FL upon pi delta Ly, and thus d can be written as under root of 4FL the whole upon pi delta Ly. Okay, as F and L upon delta L are constants, I can say that d is directly proportional to root of 1 upon y, or I can write as d is equals to constant k, that is proportionality constant, upon root y. Now we can find the ratio of diameter of copper upon diameter of iron, okay, which is equals to root of Young modulus of iron the whole upon Young modulus of copper. So correct answer for this question is option B, that is root of iron upon root of Young modulus of copper. Looking towards the next question, consider two cylindrical rods of the identical dimension as given in the question, one of the rubber and other of the steel. Both the rods are fixed rigidly at one end of the roof. A mass M is attached to each of the free ends at the center of the radius or the rods. Now, according to the diagram shown in the question, in which a mass is attached at the center of each rod, when both rods will be elongated. Okay, if both the rods will be elongated due to different elastic properties of material, the steel rod will elongate without making any precipitation change in shape, but the rubber rod will elongate with the shape of the bottom edge tapered to a tip at the center. So correct answer for this question is option D, that is the steel rod will elongate without any perceptible change in shape, but the rubber rod will elongate with the shape of the bottom edge tapered to a tip at the center.